Okay, welcome everyone to the second MITP seminar in collaboration with NITheCS. I'm happy to see the new faces and the hardcore. Anyway, today we have Izak giving a talk. Izak is a lecturer here, of course. He's the one of the few theorists that the kind of symmetric sector. Izak is going to tell us about zero-energy quasiparticles and interacting nanowire with topological Josephson junction. Please take it away.
Okay. Hello and thank you for coming and talking about a paper that I wrote with back in a master's student, Williams, who in being years almost done a whole PhD. She's about to finish in Germany. Yes, so this is not my most recent work. When I decided to talk about it, it was well, firstly, the topic is kind of mainstream. It's been a big topic in physics for about about 2 decades. Some interesting, controversial things that happen in this field, like headlines, CLA, BBC. But anyway, I won't be talking about that. I decided to talk about this because, as I say, a little bit maybe some of the ideas of topology that we should mention last week. Also, it's not something that I didn't want to talk about because COVID, and then also most of what I say, this work of mine, this work of mine allows me to do something very elementary in the talk rather than something extremely technical. So I'll spend about 90% of the talk giving an introduction to this topic that isn't my own work, and then I'll maybe spend 5% on the elementary insight that I got the title from, and then I'll spend another 5% on the part that you can see it. So I highlighted the quasiparticles in this title because that's really the key thing. There is, as you'll see, a little bit of a tension between quasiparticle and topology. Okay, so okay, so the thesis of my talk is that ideas about topological states of matter often start with a single particle nodulars that describe excitations, non-interacting systems, non-interacting systems. So in the present case, what I'm talking about, what that leads to is that one finds a zero energy fermionic orbital that can either equal or end. And this implies a twofold degeneracy of the many-body spectrum of non-interacting systems. So in any case, give me I can label by whether this zero energy part was what this full duality doesn't cost any energy, but that means a twofold degeneracy of the state of the system. Now, when topological ideas are generalized interacting systems, they usually only make statements about the many-body ground state. So here the statement becomes that the many-body ground state has this same degeneracy that the single particle Hamiltonian had. but that is much weaker property, right? Because it only tells you that the ground state of the network system is degenerate. It no longer says anything about any of the other states of the network system. So the question is whether this weak generalization is the best we can do. Yes.
So when you talk about this twofold degeneracy, can I think about it formally as a type of supersymmetry of the system?
I don't think so, no.
Because there's a fermionic zero mode that relates the two states.
Yeah, it's a fermionic system, so they are both like this. So there's no, like,
but if I add this fermionic zero mode, it's
I mean, look, I don't think that's a useful idea.
It sounds a bit.
Yeah, I don't think it's, I'm not sure it's useful. Who knows? I'm not the expert.
Because actually, what you also often see in supersymmetric systems is then that usually only the ground, if you go from free to interacting, only these ground states will remain to have a symmetry sometimes. We call it BPS states.
Yeah.
So it sounds very simple.
Okay.
Well, you are changing the family number, right? If you're changing the family number, you're almost on the overall stage. It's a math function.
I'm not getting excited when you mention supersymmetry. The guys like Kitaev also, you know, if supersymmetry was something to get excited by, I think I would we'll talk about it. But you know, it don't take away your joy. So
well, it can be useful to draw parallels. I mean, we don't have to. It can be useful to draw parallels.
Okay. Let's see. Let me present my work and then you tell me okay. So let me start by this new it's a thing that started as a toy model in 2000. It's often does these tricks with some very simple systems. You would become them. So here's the basic system. It's fermions in one dimension, hopping along some chain. So this first term is hopping from side to side. And then there are superconducting correlations, which is in the usual good way. So it is this term we have two annihilation operators or two creation operators, which is the hallmark of DCS. So you know, basically what they did is to say, well, let's just split the fermion operators into the real and imaginary parts. Right? So U is just the real part and this imaginary part. This is solution. And they have this, you know, Majorana and algebra. And if you rewrite the Hamiltonian in terms of these guys, then you get these two terms, right? And now, you know, this is highly artificial. But what we're going to do is, for a moment, we're going to think about choosing fine-tuning model, picking very special points of parameters. So if I choose the superconducting depth equal to the hopping bandwidth, so delta equals W, then only this first term is going to survive. And I represent that like this line. These lines represent the factors that there are down here. And you see U1 is coming to D3 and so on. Whereas if I set delta minus W, you have only these terms that are called UJ to UJ plus 1. Okay. Let's you know, these clearly we only have to consider one of these two cases. So we will set delta equal to delta out. Okay. Okay, let's use this switch later. So then we only have these U J plus 1 terms in the Hamiltonian. And then you know this it's kind of obvious what you should do. You should define new fermions where you pair the real part of psi j with the imaginary part of psi j plus 1. And in terms of these fermions, the Hamiltonian is diagonal. So you know, occupying any of these fermion orbitals costs an energy delta. But there's one fermion that has not been, that doesn't appear, right? So we've got these two states, these two operators in at opposite ends that we haven't used. So we can find one more fermion, and it doesn't appear in the Hamiltonian. So you know, I think that has 0 times the occupation number of that fermion. So that's a 0 energy quasiparticle. Okay, so now if you would actually, if you put this on a circle, then well, then there are no 0 energy quasiparticles. It's in state. Okay, so granted, this is quite artificial, but people got excited. Well, the reason you might be excited about it is, amongst other things, it might allow for fault tolerant quantum memory. So what we use 2 chains, right, to encode 1 qubit. So if we have, and we work with a single quasiparticle sector. So if I put this quasiparticle in the 0 energy sector of the outer chain, we'll have the 0 state qubit. And we'll call one state the one where we put it in the 0 energy orbit of the lower chain. So why do you want to do that? Well, okay, you can protect against the classical errors, so that's in sort of the conventional Moorian way. Just make sure that you control tunneling between the 2 chains, which is not too difficult. But quantum errors, which is dephasing or decoherence, they are controlled by perturbations that contain the number operator for this 0 energy mode. And if you write out that out in terms of the original fermions, you see that to get dephasing, you need to introduce an operator that directly couples the 2 ends of the chain. So if the chain is long enough, then it's there aren't any non-local perturbations like that. So one thing that makes me excited is that this thing seems to be automatically protected against dephasing and dephasing. I could also tell you about some fancier things about braiding of these guys that allow you to some quantum gates topologically. But I'll come to about that. Okay. So this thing sounded kind of artificial, right? So what can people do? Okay, so I titled this slide possible for realization. So if you follow this kind of physics for the past 2 decades or so, you will realize that it's possible is a very contentious word. There have been some scandals involving the realization of systems for Microsoft's aim to do it. So that's very interesting to look into to want to about that. Okay, so here's a possible way to realize physically. You start with just a very narrow one-dimensional or a narrow piece of metal. If the width is small enough, then you can have a single spin degenerate channel dispersion relation. Would look like this on the right. Okay. Now the spin orbit interaction that affects atomic orbitals together with breaking of some spatial symmetries. This allows you to have a solid state setup electrons that have spin orbit coupling, free motion in the crystal. So if you have material like that, then you can split these two, the spin degenerate channel, to spin channels. The dispersion would be something like this. Just display the two spin channels have dispersion relations that are just displaced from each other. Okay. Then the next thing you do is you apply a magnetic field perpendicular to the direction chosen by the spin orbit coupling. And this lifts the degeneracy of this crossing at zero momentum. But since there's no crossings at large momentums, you don't lift anything there. And then you've gotten rid of kind of degeneracy, and now you have spin is no longer an extra degree of freedom, and that's the that gives you this kind of model that I had on my first slide. And then what you do is you encase the wire in a intrinsic superconductor, and then through the proximity effect, basically out of the conductor, you induce the superconductor pairing that was the other in the model that I showed. Okay, so what changes between the toy model that we talked about, fine-tuned, and the more realistic model? So it turns out that these two fine-tuned values of the toy model, they're not exceptional. You can think of them as kind of like avatars or representatives of two phases of the general model. So these zero energy states that we see identified in this picture, turns out that they're associated with a non-trivial value of topological index that exists for the general model. So deforming from the toy model to the general model preserves that topological index. And so the zero energy quasiparticle modes remain, and what you have extra in the real model is just that now the volume quasiparticles that you get inside above the gap, a little bit above the superconducting gap, they now have dispersion. That's okay. So more about these realistic end modes. They're no longer strictly confined to the two sides at the end of the chain. They exponentially decay into the ball. So it's still localized at the ends, but exponentially decaying tail. And if you have a real system with two ends, they don't have exactly zero energy, but they have energy that the finite the energy is a finite size thing. It depends. It goes away. It decays exponentially with system size as you basically as you give these tails more room to decay into the bulk. Okay, so now the question is how to pick these quasiparticles. They're neutral, right? So this slide, what happens is in PowerPoint, you can get AI to, based on the keywords in the slide, suggest things for you, so you can sort of pick. That's quite nice. We're talking now about what are the fingerprints of these modes, and some limitations that are ruined by this question. Okay, so one of the ways that are proposed to take things through the Josephson. Okay, so what you do is you take two of these chains that are coupled by weakly. So there's no across the weakly there are no superconducting correlations. Only tunneling. And that allows the phase of the parameter to be different on the two sides. Okay. Then what you do is you connect this thing up to a closed loop, magnetic flux through, and then what the flux does is it controls the phase difference of the order parameter across these two chains. Now, usually, so what you do is, you can measure if there's non-zero flux in the loop, there is current flow, and you can measure the current instance flux, and because all the physical properties are periodic flux. That or at least the Hamiltonian is always periodic in flux with one flux quantum means that usually once you've created changed the flux by one flux quantum, the system returns to its state that you started with. So your the current that flows across the Josephson junction also have this experience. But now with these Kitaev chains, there's now some special dynamics. So when you have a flux quantum in the loop, that means that the phase difference across the two chains is exactly pi. So you have two, represent that as two real Hamiltonians. This topological mix that I talked about, it's Hamiltonian in some cases is real. So then you have this topology, and you have distinct topological phases across the Josephson junction. So two different values of the non-real values of the topological mix. Yes, what?
I'm just trying to think what this might look like in the lab. So maybe just correct me if I'm wrong. The representation of there was essentially you figure that they like almost quantum dots separated by some resistor, which you provide by going around. Set up a magnetic field right.
Sort of. I mean, as I explained to you, you don't use quantum dots. You use a thin wire coated by a conductor. And you have let's say an oxide barrier that is separating two of these guys end to end, and then you just make the rest of the thing with wires, and you switch it. Okay, so then you have you have two domains with different values of the topological mix. Non-trivial, and there are general topological arguments that say whenever you have something like that, you expect a zero energy mode associated with the inputs. Okay, So in our toy model, that's very easy to check. Of course, in the real model, we also find it with physics, but let me just show you how it works in the toy model. So here is the picture with delta equals W on one side, and the other side is delta minus W. So these dashed lines here in the middle, these are the two tunneling amplitudes from right to left and left to right. These big lines are the carbon status or inversion slide. Okay, so you see that these two yellow modes that I have indicated here, they only appear in the Hamiltonian and particular linear combination. The same with the two blue modes, right? Which means that you can form complementary linear combinations that are orthogonal to these two, which I've done here, and I've constructed a fermionic molecule from it, which we'll see in the base. And this includes the Hamiltonian. So here we have another. So we have a zero energy quasiparticle orbital localized around the junction. Okay. So now, what's the impact of this on the Josephson? Well, so if I'm at some arbitrary value of the flux, these considerations don't apply. What I've drawn here, the yellow is the ground state energy, the blue is the excited state energy. At fluxes different from pi or 2pi, they're distinguished by the occupation of a quasiparticle. For a general flux, this quasiparticle is not localized only at interfaces, hybridized begins in interface. Then, when we write an alpha flux quantum, these two levels they become degenerate. Okay, so if we slowly tune the flux, and it's always slow, we do it because we don't tune things into the into single particles. Yes,
So this tuning of the flux is adjusting the slowly down.
It tunes the phase of the ordered parameter, the phase difference of the ordered parameter between the two junctions. Look between the two junctions. And when the phase difference is exactly pi, you have a zero energy quasiparticle. Otherwise, you have a quasiparticle that is in the gap, but it has a finite. Okay. So now what happens is if you tune the phase and start out in the ground state, then you evolve after one flux quantum spectrum, the system, the Hamiltonian is returned to its original value or its original form. But you have ended up in the excited state, and you have to create another flux quantum to put you back in the ground state. So that means that your Josephson effect, you look at the Josephson current, it's not going to have a periodicity of one flux quantum, but of two flux quantum. That's if you, if you somehow lost this zero energy particle, don't go all the way to zero, then you're going to be back to one flux quantum periods. So that was the proposal for detecting zero energy particles. Okay, but I said that this model, with delta, this is a meaningless real model, but it still indicates actually fits. So the superconductivity I said, that's typically proximity superconductivity that we get from some coating. There are, however, still electron topology between the electrons in the wire itself. And because it's a one-dimensional system, it's not necessarily well screened. So you have to wonder maybe about these residual interactions. And the simplest model then is make them short range. Just using the electrons on adjacent sides. Okay. So when you add interactions like these, then there are topological arguments that still guarantee the robustness of the ground state generacies that we found. But as I said before, in the non-interacting case, it's actually many body state of the junction that has fourfold degeneracy. That's because we have these two quasiparticle orbitals, and they are questions commuted with the Hamiltonian. So you for every energy you can ask is the one quasiparticle orbital that begins full energy, and you can ask is the other one full energy. So now the question is, are there still non-interacting zero-energy quasiparticles acting system? So is there still fourfold degeneracy of all body states? Or if we want to do quantum information processing, are we compelled to work the ground state manifold? If that is the case, then what's called quasiparticle poisoning could become a problem. Okay, so you might say, well, okay, fine, we have to work the ground state manifold. That's fine. We'll just make sure that the system's cold enough. You can go down to 10 or 20 Kelvin cryostat, and superconducting transition temperatures like Kelvin or something like that. So you don't worry. But something that's not completely understood yet is that in these small systems, like we will struggle with it, you always seem to have more quasiparticles than you expect from the temperature to some sources that have been identified like gamma rays, some stuff that's hard to block. And so you just end up always having two excitations out of the gap in these systems. You try very hard to get rid of it. So here's the picture. So in the interacting case, we know we still have two degenerate ground states, two independent states that the most possible. Okay, but now if we have really non-interacting zero-energy quasiparticles, then this situation that I've drawn is fine for quantum information processes. There are some quasiparticles here, but I've created this zero-energy equal to be empty, and these guys they don't interact with the sky, so they just stay here. But if there isn't a version of the non-interactive quasiparticle in the system, then there's nothing to prevent this process from spontaneously happening, and the zero that I've tried to encode becomes one. Okay, so quasiparticle poisoning is a real problem. Systems, there are lots of sources. Electron proton interaction is always a source. The question here is the residual interaction between electrons in the wire also a source? Okay, so another reason I chose this topic, I could mention someone that I don't know, you guys with street years, Paul Henry. Okay, so yeah, so I chose this so I could at least cite one guy that you know. So for the single chain, maybe shown in 360, but in fact we still have strictly non-interacting zero-energy quasiparticles. We just did it by explicitly constructing. Okay, so this huge base that I'm showing you here, this is the expression for this n-state Majorana operator that was just a linear combination of sine 1 and sine A in the toy model. Okay, so actually getting to this expression is not that tricky. It's sort of a brute force method that gets you there. What's really tricky is to show that this thing is can be normalized with the square root of the spiral. So you can make it like
so in comparison with the toy model, can you say again what it means to not be interacting? That you're changing the value of delta?
No. So remember, interactions mean not something that's not quadratic. So
yeah.
So here's the interaction term, right? So it's the charge on side j multiplied by the charge on side j plus 1.
So you see that's wave function is still commute or
So this operator state, this for a semi-infinite chain, this operator would commute with the full Hamiltonian.
it's an operator, not a state. It's an operator.
It's not. It's an operator.
But it creates. So what does it do? It creates actual chain and creates.
So it's Majorana operator. So it's one half of fermion, right? It has the same algebra as A plus A. So if you have a very long chain, so this thing in case of 2 exponentially to the box, you have a very long chain, then up to exponentially small fractions, start one of these at each end, and you can take U1 plus IU2, that behaves exactly like the fermionic creation operator. So this is zero unit quasiparticle position.
But that is localized exponentially.
Exactly, yeah, at the 2 ends, right? Exactly like in the twin. Okay,
and these j's here are that they do.
So here they are defined. So they come from the parameters of the model. So it's basically
so is there some notion of integrability?
Yeah. So okay, I'll comment. Okay, so the one thing I want to show you is that this union operator inherits some of the properties of the Toy models one from the fact that you have this unpaired sigma operator in pairs of sigmas. And this sigma operator, that guy has this view that we used in the past on it. So this is this, and this is actually quite okay. So I tell you this slide to show that there is some real mathematics, for example, some real expressions like I always see in theory talks, because everything else useful. Okay, so what it means we found Majorana again construct exponentially localized on the end of the city chain that we so there are different so you actually find different ones depending on the hierarchy of whether the factor strength dominates or the helping dominates or the superconducting pairing dominates. So in the case where that we think well, the case where the extrinsic superconductivity stronger than intrinsic interactions. This UN behaves like the fermionic operator that the non-interacting chain. So in a long chain, a single non-interacting zero quasiparticle will be associated with the use at the ends of the chain, up to explanations. Okay, so what I'm now going to move towards is showing you that this result of bending implies also that there is another zero energy quasiparticle within the lattice. Remember, we're looking for two. We found one now associated. Well, okay, we haven't found anything yet, but Penny talked about single chain out of Josephson junction. And he found one split between the ends. Really interested in the chain with Josephson junction. Okay, so we need to briefly talk about the states of the system. So the Hamiltonian has fermion number parity description. So the total number conservation is really parity even with odd number conserved. And you have a kind of particle conjugations. So you can define an operator that takes create operators, annihilation operators, uniquely, and it acts on these real identification because fermions are just changing the sign, which is the sign the same. And you can find it to have the pattern that's depicted in this figure. So it's alternating for the use along the one chain and along the other. And same for the central beads, it's kind of staggered. So we do it the on the same side, the transform signs. And this is symmetrical. The emissions operate on one Hamiltonian, we do the same when we do that. Okay. So here is the 5% of my talk where I give you the elementary observation that we follow this with. Okay. So first thing, these two operators that can be found associated with the two ends that are away from the junction under parity, they transform into minus themselves. So change from one number by one. As I said before, they are Majorana operators. So we have two of these constructed fermion. They inherit the particle-hole conjugation properties from the bare end operators that I showed you before. And this implies that I can construct a single fermionic quasiparticle orbital that's localized and split between the two ends. Yeah, it's exactly how I expect, but the quantum conjugation, the fold state goes to the end state. Okay, so this is the one part of it. Okay, now what about the other one? Okay, so this is my observation that the existence of this one at the end can be used to prove the existence of another. Okay, and this is how it works. So let's label our states by quantum numbers of energy or fermion number parity +1, and or where this end state is occupied. Okay. So because this is a zero energy quasiparticle, each state has topologies. Okay. So here are the give me a state with give me a state with zero quasiparticles in this end state orbital, and I apply the creation operator to the end orbital. And I get one whose parity or number parity is changed, and I've got one fermion in this spin orbital. Okay, so now I'll take this state that I've used. I've got anything in this end orbital, and it's got the parity it's got, and I apply particle-hole conjugation. Because particle-hole conjugation is symmetric Hamiltonian, I get an ion state. It has energy, the same energy as the one I started. So here I'm going to assume that my chain consists of the two chains together consist of an even number of sides. I could have assumed the alternative and given you, there's a fork in the road, both forks should end up proving the result. So I'll just go down one. Okay, so we'll assume even. Then that means that the size that I got by applying P has the same number parity as the state that I started. The reason for that is I've got two end orbitals, right? And I change every full orbital into empty orbital and every empty orbital into a full orbital. I go from n particles to 2n minus n particles, which has the same number back. Okay, so this state I've created has a number parity. But I think this is now an important thing. The number operator for the end state goes into 1 minus itself on particle Hall conjugation, right? N goes to 4 n. So that means this size state has an eigenvalue 1 for this number. So you see it's a combination of problem numbers that we haven't found yet. So this is a new state. It's not one of the two states that we had before. Okay, so we've got another zero, we've got another state at the same. And then it's easy to get the other one, remove the polygon from the end state. So there you have, the fact that the existence of this end state implies the existence of another zero energy non-interacting quasiparticle, and you have fourfold genus. Okay, so that's the main insight. Then we spent a year asking ourselves what happens if we break particle Hall symmetry that was essential in this proof that I gave you. It also breaks integrability. What actually happened was started working with the students and we were looking for an excuse to learn numeric technique. So we put learn numeric technique when we picked this problem. So this numerical technique allows you, well, what we exploit is the fact that in 1D systems, the entanglement entropy, at most goes moderately with the size of the subsystem. And people have used that to build a numerical method called the density matrix normalization group that gives you accurate numerical results in a controllable way with no energy excitations in expansive quantum systems. So we wrote our own code and we implemented it, and we looked at adding a chemical potential which has particle and we saw that below some critical value, it seems that we still have all the lowest excitations that we can at least this fourfold genus. It's not perfect. This is a finite system. It's got something like in 60 sides or something like that. So that's what we can do with a reasonable amount of time. And then if you make the chemical potential too big, then you clearly lose this fourfold genus solution to be a transition. So it seems that there's a bit of a mystery here. Something that was really essential in our proof, symmetry that we required to make the proof, and which we could figure out no way around. When we do numerics, we seem to see that in fact it doesn't have an effect on the breaking. It doesn't have an effect on the result.
Sorry, could you remind me what happens if we equal 0?
So mu equals 0 is the test that we've been looking at the whole time. That's when you can prove fourfold genus. Yeah.
Oh, so these states are more or less going to be the same as.
Yeah, in a finite system, it's going to look like this also.
Just the numbers are going to change, but
yeah, the numbers are going to change, but still you're going to get this fourfold genus. Okay, so then these finite size effects that give you the slightly generous lifting there's actually there's some interesting physics associated.
So I make a listen from the calculus. If I see this calculus, I know these are edge states.
So in this calculator, you can look at where. Yeah, with the code gives you
So the code gives you the actual.
you get the actual ground state wave function based on some matrix product state.
So presumably the code gives you a lot of other things. So now you focus on the one.
So
From the above.
no. So you have to do this calculation. You pick a state. So you want to get ground state, the perfect cycle state. You do your numerical run, which takes a day, and you get the energy of that state. And you
But you're not diagonalizing the whole chain.
you're doing it's not you're doing things like natural so on. So you it's with diagonalization between the eigenstates. It only works with the lowest eigenstates. And you have to do them one at a time.
How many sites do you have in the chain?
These ones you can see out here are way to 80 sides each side of the junction.
And that takes a day.
I might be wrong, it might be 6 hours or something like that. It takes a long time, yes. Okay. So I wanted to say something about finite-size dates. So okay, so what we have superconductivity, which is sort of like due to the effective interactions that are mediated by phonons in case of superconductor. And we have repulsive interactions between the electrons, right? So now, not surprisingly, this gives you when you work out a gap that's lower than the non-interacting gap. Okay. Now, in the non-interacting system, for a given gap, you have a given a decay rate for this tail that the edge states have into the ball, which is also what determines this finite size degeneracy lifting. Now, the interesting thing is that if you pick an interacting system that has the same actual gap as a non-interacting system, so you have stronger superconducting pairing in the interacting system, but that is sort of like degraded by the electron repulsion, and that gives you the same gap as in the non-interacting system with the weaker superconductivity. You find still the larger finite size correction, the same system size than in the non-interacting system. So these extra interactions, they produce extra end-to-end correlations that aren't there in the non-interactive system. This is what this picture shows. So at this dotted line, we look at the exponential decay of the finite size degeneracy, and we got it accurate. And then we ask how big a gap do I need in a non-interactive superconductor to get the same decay, large gap in the cost of decay. And it turns out that so this over here, this is the gap of the interactive system. So non-interactive system with a smaller gap between the same finite size correction, which means that there are stronger end-to-end correlations. Okay, so then we finish with the following mark. So last year, I worked on the stuff 2 years ago, and I didn't really look at it again. Then last year, I noticed the preprint, and so if you look at these institutions, they look like a Majorana end state between the two coasts of the US. So you'd expect fault tolerant, but I'm not sure it is. So but okay, so they said today the stability of these things are only be explored at physical system. Here we explain the notion of strong zero modes bounded between two systems in unifying framework. So they were not aware of my work. So this came to the first time when I wrote on those emails, I say, you say that no one's done this before, but I'd like to revise that statement, like that. Then we look at really non-interacting situations. Anyway, so I wrote them. I said, we very numerically investigate the breaking of the particle symmetry, guiding it large kinetic potential. But we find that you break the symmetry, you still have the fourfold degeneracy, and it's always puzzled me because I think just my proof. If you have any insights, I'd be happy to hear. And the response was, well, one of the guys, like you, I'm quite surprised by the observation that the degeneracy survives the particle integrating. I wonder if it will survive the full spectrum, which is obviously extremely challenging to test. We may, if the email talked about how it would also be kind of possible to do analytically. So that's the point. There seems to still be some puzzle. People don't know what the answer is yet. It's a bit mysterious, this robustness of this fourfold degeneracy that extends all the way up the spectrum. The way I proved it, or I could prove it, it has the feeling that there might be something topologically going on, right? So I'm just looking at N, and I'm able to predict something that happens far away. So there's something non-local, which makes me think of topology. But as far as I know, ideas about the topology in condensed matter systems that gone under the name topological states of matter have not got anything to say about this so-called strong zero modes. So who knows? Maybe there's some still some topological constructions to be discovered. Okay. Thanks.
Thanks, Izak. Any questions?
So as you approach this point in what you call neural thinking, where you stop seeing the degeneracy, what happens? Like how do what this critical value, let's say,
So I didn't have but it looks kind of like this. So here I break the fourfold degeneracy by going across a phase transition by making reacting strong. So you see what happens is that so this is the this and this is the finite size version of the fourfold degeneracy. And you see then what happens is that, well, at least for the ground state, you go to 2 in this case, because for this, when you switch on actions, you're still going to have the in states. So just like the states rearrange themselves. It's a quantum-based transition, and it's
is it a critical exponent?
It's an unusual quantum-based transition because it implies an thermodynamic an abrupt change, not just the ground state, but every excitation in the system. But what must happen is that this tail, this exponential tail by which these modes decay into the bulk, that this big scale diverges, and I'm sure there will be a critical exponent associated with that.
But then maybe some CFT understanding boundary CFT.
Well, I mean, Paul Sweeney would have known.
Something for this case, right?
Yeah. So he comes. Well, I mean, but he studied this transition.
So you mentioned that there were lots of controversies experimentally. These things. What is the controversy? Because maybe
okay, so there's this very good group that I tried to do it because I studied it out, and
They were for a long time with the leaders of the field who came to do experiments on qubits with superconductivity and so on, headed by a guy called Coleman. And so Microsoft gave him a lot of money from the institute, kind of like at Santa Barbara. So there was one in Delft, and there was also one in Copenhagen. They recruited like best experimentalists in the States, Charlie Kane, he was from Harvard. And so these guys were going to find these Majorana states. And then in somewhere in the tens, I can't remember if it was 1600s or something, government announced that they found it. And this four-five-dose effect played a role in discovery. Then there was this guy who came from the Congo group, but looked at this data and also knew that these guys, they're very ambitious, so they're writing, they want to discover something. He started analyzing their data and thought that he saw things that didn't make sense. So there was a long fight about getting access to all the data. And then in the end, he convinced proved that what happened was that PhD students that took measures basically glued things together in the wrong way and saw a jump in something that would say that it is zero not when in fact things were smooth, it was just an opposite problem. So they didn't see it. So then there was a independent investigation and the nature was the business, but they withdrew this paper, the discovery of the numbers. This, set the view back a lot. So, these guys suffered reputationally. Apparently, they will always be unhappy with Microsoft. So, Charlie Marks left Copenhagen. I know people were very envious, but it's very hard to find accommodation in Copenhagen. Part of the deal was in an apartment in Harvard, whatever. He left, said that was the worst 10 years of his life. He was taking 7 days. Anyway, so that was the status for a while. Then last year, still this Microsoft group, they released a new paper, which they say they have this very sophisticated AI assisted way of looking at all the possible sources of noise. They train AI to spot when you really have one of these guys versus all the ways that could go wrong. And by the way, so these things are the reason why these experiments are hard is because this kind of superconductivity disorder has a much worse, much more deleterious effect than for the normal SS. Anyway, so then they announced they have this very sophisticated way of doing it. They convinced themselves that they found these things. They wrote a long paper, so I think it PRB, but said, I think they said the release can look at details, but they're not going to publish the details. They discovered these things because there are patents pending. So they can really controversy whether this paper should be published or not, whether that, because it's not reproducible. PRB eventually decided to publish it. Obviously that's another big controversy, and coming from the people who made the false claim the third time round, so this stuff is just getting controversial.
Okay, I think this is a good one to end. So let's thank Izak. Another new seminar next week. We'll get the invitation, summary.